Okay. Okay, welcome to the second part of the conference of this day. The first talk of this session is in charge of Michael Janssen from the University of Minnesota. The title of the talk is Quantum Kinematics, a new framework for handling probabilities. Go on, Michael.
Okay, thank you very much for the invitation. Everybody can see my screen. I hope you had a chance to read my abstract. So what I'll be doing for the most part is to talk about like the correlations you can get with the proverbial Alice and Bob performing measurements on two spin half particles entangled in the singlet state. And I'll represent sort of the class of correlations that you can get in that kind of, or like I should say, in a setup that was suggested by David Mermin, where Alice and Bob both choose from the same three observables that they're going to measure. And I'm going to be looking at the kind of correlations that are allowed in that setup if you just restrict it to like anything that's non-signaling, anything that can be done quantum mechanically, and anything that can be done like with local hidden variable theories. And I'll show you that there is a nice three-dimensional like graphical representation of that. So the work is based on a book that I wrote with Michael Janis and Mike Cufaro. So here is the three of us like in Minneapolis a few years ago. And since the names of the three of us are sort of variations on Michael, like this has become known in certain circles already as the Three Mikes Manifesto. The book will come out in January. It's in the series Boston Studies in the Philosophy and History of Science, and its official title is Understanding Quantum Raffles. Now, the book was inspired, and this is the banana that you'll be seeing as my background image throughout the talk, by this book by Jeff Boop, Banana World, Quantum Mechanics for Primates. And here you see a picture of me and Jeff at a conference in 2019, like in Santiago, like following actually this conference in Cordoba in 2019, where I also gave the talk and had a great time. So I should also like put in a plug for like the sequel to Banana World, which is one of my favorite books. It's a serious comic on entanglement by Jeff and his daughter Tanya, a graphic artist, called like Totally Random. All right. So here's the setup I want to talk about, right? And so so instead of talking about spin half particles, I'm going to be talking about like entangled bananas, like as in honor of Jeff's book. And so what we start out with like a pair of entangled bananas, right? So they are described by the usual, singlet state. And then like Alice and Bob, decide like on one of three ways to peel the banana. And so this is basically just window dressing for like, they have like a Dubois magnet with which they measure spin in a certain direction. And now they're going to hold their banana in a particular direction, while peeling it. And then they take a bite out of the banana and determine whether the banana tastes yummy or nasty, right? So, and the results are we're going to put like in a correlation array, which is really the workhorse of Jeff's book, Banana World. And so here you see like, Alice can measure A, B, and C. Bob can measure A, B, and C. They can only find, plus or minus corresponding to a yummy and nasty. And what you see is that if they happen, all the runs in which they happen to peel the same way, they find like a perfect anti-correlation. And in all the runs in which they peel different ways, they find like an imperfect, like positive correlation, right? So look at AB. So there is like a, like a 3/4 chance of them finding the same, 75% chance of finding the same, and only a 25% chance of them finding opposite. And the question is like, like what's how to account for this. Now, so this is like what you get in this Mermin setup if the angles between like the peeling directions are like 120 degrees. Now you can consider like a more general correlation array of this sort, and we're going to consider like any array that would like this that would be non-signaling, right? And in order to guarantee non-signaling, if you have these anti-correlations like on the diagonal, it has to be the case that you get uniform marginals, and you do that by making sure that in all the off-diagonal cells, the sum of both the two rows and the two columns is equal to a half, right? And so since the probabilities, of course, also have to be like numbers between 0 and 1, you get that you can parameterize this by these chi's that I have here, and these chi's can run for all the way from -1 to +1, right? And so I can characterize this correlation array by having three of these parameters for three of these cells, right? This thing is also going to be symmetric. It doesn't matter if you switch like A and B. So that's the story here. And you see that in the special case that is considered by Merman, that these chi values are equal to -1/2, right? So stick that in here. If you put in like -1/2, like this would be 3/2, so this would be 3/8, right? And this would be 1/8, right? So you recover that Merman correlation array. But again, like this is a more general form of it. Now, what we're going to try and do is to see what a subclass of those correlations we can simulate like with a raffle, right? And the raffle is our toy model for a local hidden variable theory. And so we imagine that you have a basket with a bunch of tickets in it, and the tickets like have the outcomes for like all possible measurements that Alice and Bob can do. Now look at the first ticket, like we know that if they measure the same way, that they find opposite results, right? So like the results on 2/2 of the tickets better be opposite. The way it works is that you take a ticket, you rip the ticket in half, and then you randomly decide like which one goes to Alice and which one goes to Bob, right? So a ticket where you just switch the left and the right side does not give you a new ticket. So with that said, there is like 4 different tickets, right? So it doesn't have to be the case that all the pluses are on one side. You could have a case where 2 of the pluses are on one side, and like with 1 minus. And again, there is 3 ways of doing this, right? So you have the minus here is for C, here the minus is for B, and here the minus is for A, right? And again, keep in mind that it doesn't matter which side of the ticket you're looking at. Now, we can easily see, like if you had like single ticket raffles with just like a basket with one type, what these chi parameters would be, for your correlation array. Because you can see that if you have this ticket, no matter whether you take like AA, AB, or AC, you always have like a perfect anti-correlation. And that means that these chi values have to be like +1. Like maybe I should go just like back here, right? So the moment that that chi is +1, right, then you see you have an anti-correlation. The moment that chi is -1, you have like a perfect correlation. So okay, so that's easy. Now look at this ticket there. It's a little more complicated. So for AB, you see that there's still a perfect anti-correlation. But if you now look at AC or at BC, you see that there's a correlation. So you have -1. And the same is true for C and D, right? It's just that a different parameter will get like the plus, and the other 2 parameters will be minus. And here then you immediately have like a Bell inequality of the type of the Clauser-Horn-Shimoni-Holt variety. And you can see that, like the sum of these 3 parameters is 3 for ticket A and is going to be -1 for all other tickets. So if you take like an arbitrary mix of tickets, right, you would always get like a value somewhere between -1 and 3. So, and you see that Merman's example where where these 3 chi's are -1/2, so that would be, if you sum them, would be -3/2, violates this inequality. Now, the nice thing about this is that you can come up with a very nice geometrical representation of the situation, and that is essentially due to Jeff's longtime collaborator, now deceased, unfortunately, Itamar Petowsky. And so, first of all, we start out with like representing these chi values. They can run from -1 to 1 in like what is called like a non-signaling cube. Remember, like, this was like the general form of a correlation array that is non-signaling. And you see that these tickets, like they're represented now by vertices of that non-signaling cube, right? So it's these 4 points, right? A, B, C, and D. And a mixed raffle would be represented on like points that are like somewhere in between, right? And once you have, so imagine like, you have your basket with tickets. So if you take this and you put a certain mix, you can end up somewhere over here. But and you take a mix of like, D and C, you get up somewhere over here. But you can also like, now mix those, right? So you get all of that, and you can also like mix and match, and get like on the inside of this thing. So this is like what is known as the classical tetrahedron, and this is like a very nice way of geometrically representing what a local hidden variable theory can do. The Bell inequality only corresponds to like one facet of this tetrahedron. It just says that you can't be behind that plane like B, C, D, but you see that there's 3 other forbidden regions that you would also have to spell out if you want to define fully, what is and what is not allowed. All right. So now in what is allowed by quantum mechanics, right? And so in quantum mechanics, the result that is predicted by quantum is that these chi's are just given by the cosine of the peeling angle. Right? In a way, this is like very satisfying, right? So classically, you see that these chi's with these tickets, they're always going to be +1 or -1. But wouldn't it be nice to have like a theory that just allows like a continuity of values between -1 and +1? Quantum mechanics gives you just that, right? And so it's the cosine of the angle, and that cosine, of course, is the inner product of like unit vectors in these different peeling directions. All right. So if you think about this correlation array, you see that the entire correlation array can be like characterized by these parameters, right? These chi parameters, and we can also introduce them for the diagonal cells where they're just 1. Okay. So I'll define this more carefully later on. But these chi's are like, what can be called like anti-correlation coefficients. That's for now, it just hinges on 3 values, right? If chi is 1, we saw you have a perfect anti-correlation. If it's -1, you have a perfect correlation, right? So it makes sense that the anti-correlation coefficient is then -1. If chi is 0, you have no correlation at all. Now introduce now like a matrix, an anti-correlation matrix of just these chi values. And you can write that again, like in terms of these inner products of these unit vectors. Now, this is a Gram matrix, right? And it's a well-known property of the Gram matrix. It doesn't take too much to verify this, but in the interest of time, I'll skip that. We know that the determinant of that matrix is going to have to be greater or equal than 0. And if you just calculate the determinant of this here, you now get this condition. Okay, so quantum mechanics like imposes the condition that that this inequality has to be satisfied. Right. So put differently, right? So quantum mechanics, once you have the idea that these chi values are the cosine of the peeling angles, so you can specify like the correlation array by just giving me 3 angles. But basic geometry tells me that once I pick 2 of these 3 angles, it puts constraints on the 3rd. And this is the constraint that it imposes. And if you now like plot this, you see that what this picks out is an elliptope, or what has been called sort of a fat tetrahedron. You puff it up a bit. The lines here are contained in it, but like in the middle, like it's blown up a bit, and we'll call this like the elliptope inequality. And this then is sort of the quantum analog of what the CH-SH inequality in the case of the Mermin setup, right? And remember, for the full specification, we don't need just 1, but we need 4 of those inequalities. Here, we only need 1 nonlinear inequality. And this inequality is satisfied by Mermin's example, right? I mean, if you just look at it, you see that if you put in a half, you get like exactly that this is going to be equal to 0. So this is actually a neat result, I think, because like it gives a concrete example of like a cartoon that you often see about how the convex set for non-signaling, quantum, and local hidden variable theories are related. Right. So here's a cross section of our drawing, right, with the non-signaling cube, the elliptope, and the tetrahedron. Right. And now compare that to like the cartoon that is in Banana World, right, where you see like the non-signaling cube with like like the maximal variation, like a Popescu-Roerlich box, right, with a super quantum correlation that still is non-signaling and doesn't violate special relativity. Then you have the quantum convex set, and then in the middle you have the local polytope. And the beauty is that in this particular example of the Mermin setup, you reproduce like now exactly what you just have as a cartoon in general. All right. And you can play the same game for bananas now, entangled bananas of higher spin. And so in our book we do this, right? So here's what the correlation array looks like, just one cell for a spin 1 banana. The anti-correlation coefficient, it turns out, which is defined like this. I'll get to that in a moment, like stays the same, is still the cosine. If you go to 3/2, still the same, cosines. So all these correlations are all like constrained by the exact same elliptope inequality. That's not the case if you now try to simulate them with these raffles. So we saw that, like if you do this for spin 1/2, you get like the tetrahedron, right? So you get something with like 4 facets like this. If you now go up to higher spin, you see that you get a little more structure on these facets. So this is what it looks like for spin 1, and notice that this point here is going to touch the elliptope. For spin 3/2, it's not going to touch the elliptope again, but for all integer spin, it will. Right, and you see this gets more and more faceted, more and more vertices, and like it's very suggestive that if you go up to higher and higher spin, it gets more and more close to the elliptope, but never quite gets there. Right. Now, so far it may seem that this elliptope somehow captures like something special about quantum mechanics. In particular, like we used, sort of as hidden, like in what I showed you, but we used like, the Born rule, the Hilbert space formalism. But in fact, this inequality is not new to quantum mechanics at all. It has been known to statisticians since the 1890s, and it's basically a general constraint on the correlations between any 3 random variables, right? Which also like, makes it understandable that even if you go to higher spin particles in quantum mechanics, you'll never get out of the elliptope. So this work is due to Carl Pearson and mostly to Utne Yule. So Pearson, of course, these days is mostly remembered for his dubious role in the eugenics movement, but he's also like, like a very important character in statistics. So let me run through this quickly, right? So now we're talking about sort of arbitrary random variables with sets of possible outcomes that I'm going to keep discrete. And in fact, I'm only interested in a case where you have a random variable with only 2 outcomes, like, yummy and nasty. And so I'm going to restrict my attention to what we call balanced random variables. And that just means that if x sub I is a possible value, minus xi is 2, and that the probability of xi and the probability of minus xi is the same. And that simplifies matters, because that means that in that case, the expectation value is going to be 0. And that simplifies like some other variables, some other quantities that we're interested in. So we're looking at the variance, right? So the expectation value of x minus the expected value of x squared. If the expected value of x is 0, then the variation of x is just the expectation value of x squared. The standard deviation is the square root of that. And then the covariance, again, like, in general would be like the expectation value of x minus the expectation value of x times y minus the expectation value of y. If these 2 expectation values are 0, then that is just going to be equal to the expectation value of x times y. And I now introduced like what is called the Pearson correlation coefficient, which is just the covariance the Pearson correlation coefficients of x and y is the covariance of x and y divided by the corresponding standard deviations, sigma x and sigma y. And so if x and y are balanced, this is just the expectation value of x and y divided by these standard deviations. And you can immediately see two properties, like, you know, the Pearson correlation coefficient of a variable with itself is just 1, and it doesn't matter if you look at the correlation coefficient xy or yx. And I'll now prove for you that any triplet of such variables is going to have to satisfy this ellipto inequality, and this was shown by Joule in the late 1890s. So here's one way to do it. Like, you know, consider, you know, for any triplet v1, v2, v3, like this quantity over here. So I'm looking at the expectation value of some expression squared, so I know this is going to be greater or equal than 0. And now I'm going to work this out. Okay, so I take, like, you know, like this term times the rest, that gives me this here, right? And so note that I now get, like, you know, v1, and then I have like x times x, right? Expectation value x squared divided by sigma x squared, and then we have the x times the y, the x times z, and then you have similar terms for, like, if you now do the v2 y over sigma y and v3 z over sigma c. And you see that in here, like, you have like all these Pearson correlation coefficients. It just looks like that, right? And I can write this like a little more concisely and compactly as just this matrix with these Pearson correlation coefficients sandwiched between, like, you know, the column vector v1, v2, v3, and the row vector v1, v2, v3. And remember that this thing has to be greater or equal than 0 for any value of v1, v2, v3, which means that that matrix rho is positive semi-definite, which means that the determinant of rho has to be greater or equal than 0. And it follows that, you know, that's just the ellipto inequality, right? So there we have it again. Okay. So now look at the special case that x, y, and z are the taste of Alice's banana, right, in this experiment in the Merman setup, right? So x is the taste of Alice's banana when she peels in the A direction, y is the taste of Alice's banana when she peels in the B direction, and z is the taste when Alice's banana when she peels in the C direction. All right. So now the obvious problem is that as Popescu points out in the preface or the foreword of Banana World, a banana can only be eaten once, right? Once it's peeled, it's peeled. Once it's tasted, it's tasted. But we'll see there's ways around this problem. So first, I note that these variables are balanced, right? So we have to now give them some numerical value rather than just yummy or nasty. But, you know, inspired by spin, you know, like instead of having like a half H bar, we now have like a half like a B bar, you know, which I call the banana split, which is just Boop's constant B divided by 2 pi. And we're going to pick units such that B bar is equal to 1. And so then, you know, we see that these variables are perfectly balanced. The expectation value is 0. The variance, right, so is like, you know, half the time, like, you know, it's the product is it's 1/2 squared. The other half is like, you know, minus a half squared, and that adds up to 1/4. The standard deviation, take the square root, that is like a half. Now the covariance here, it's a little trickier, and what we're going to do. And like, you know, if you're squeamish about this, like we did find a way to avoid like this counterfactual reasoning, but I think it's perfectly innocuous. We're going to use the opposite if we want to find the covariance of the variables Alice's taste of the banana when peeling A and the taste of Alice's banana when peeling B. So have Alice peel A and then have her use minus what Bob finds when he peels B as a proxy for what she would have found had she peeled B instead. Okay. And so basically, like, you know, that, so we calculate this thing here, and we can use our correlation array to figure this out, right? So we have like if the tastes are the same, we get like 1/4. What is the probability of that happening? Well, you need to add these two things, right? So that's a half 1 minus chi AB. And then, you know, like if they're opposite, it's minus 1/4, and the probability of that happening is this. If you work this out, you see that this is 1/4 times chi AB. And if you now like calculate the Pearson correlation coefficient, you see that that is exactly equal to chi AB, right? I already took an advance on that result, calling this chi AB like an anti-correlation coefficient, right? And the anti is because of this minus sign. All right, so the ellipto inequality, you know, I can just now write for this for these particular variables, right? So in terms of these rows now, rather than these chi's, and so this is just exactly the same. But there is a few problems here, right? So the first problem we already dealt with, like how do we determine the taste of these two Alice peeling A and Alice peeling B in one run? Well, you know, have her use Bob's result as a proxy for one of those, right? Now, the second problem is like, you know, we can only do this for two peelings in one run. Well, that's not a big problem either. Like you can just have different runs, right? So if you think about it, that's what we always do, you know, like if you think about the early tests of the CHSH inequality, they weren't switching the settings like, you know, from run to run. They just take measurements for one pair of setting and then fill in with another pair. That's all perfectly fine. So that we can do. The third problem seems to be a lot nastier. And there the problem is that, you know, we derive this ellipto inequality from the condition starting that the expectation value of this quantity is always greater or equal than 0, right? But the point is that we cannot determine the value of this in one run. And it would seem that if all these three variables like can only take on values like plus or minus a half, that yes, it's going to be greater or equal than 0, but that inequality is not tight because, like, you know, like we could easily, the smallest we could get this is to something like, you know, a half, like, you know, like you take plus and minus here, and then we have a quarter. So this took us a while to figure out, and the answer actually hinges on like, you know, like an interesting property of quantum mechanics, namely that in quantum mechanics, it's perfectly possible for a sum to have a definite value, even if the individual terms in that sum do not, right? So the simplest example I can think of is like, you know, the Hamiltonian for a harmonic oscillator. Clearly, P and Q cannot have like, you know, definite values at the same time, but, you know, the Hamiltonian can. And so to look at this a little more clearly, right? So we're looking essentially at sort of a sum of like Hermitian operators, a linear combination, and that in and of itself should be like a good operator. And so if you introduce like, you know, now like in analogy with a spin vector, like a taste vector, you can write like the taste in the A direction as like the inner products of like T with like the unit vector in the A direction, same for TB, same for TC. And then the inequality becomes this, and you see that we're inner producting like the taste vector with this vector, and this will be 0 whenever this combination is 0, right? And so if you pick the right peeling directions for starters that need to be in one plane, you can actually like achieve that. So this inequality is tight, and this result applies to so the general result of Joule thus applies to this quantum example. All right. So what do I want to conclude from this? Okay. So the point is that this ellipto inequality that we derived first within quantum mechanics from the geometry of Hilbert space can also be derived without quantum mechanics as a general constraint on correlations between three random variables. And this distinction, like actually we got from within, from without, from a song by Bob Dylan. So the message then, this is the big message of the talk, is that what this suggests is that the basic Hilbert space formalism of quantum mechanics is just a new framework for handling probabilities, right? And so this take on quantum mechanics, which has been dubbed boobism, as a pun on cubism by Rob Ramishevitz, belongs, I think, to a class of informational makeovers of the much maligned Copenhagen interpretation. And so in order to make that clear, like I want to talk, I mean, I'll take 5 more minutes to make the point. And this is far more speculative and tentative than what I've said so far. I think it's best to sort of think in terms of like a genealogy of quantum interpretations. And so we got like 2 versions of quantum mechanics around 1925-26. First, we had matrix mechanics, and Heisenberg's big discovery was that these problems in spectroscopy that he was running into just call for a new framework for dealing with physics, just as like the problems that people had run into in electrodynamics around the turn of the century called for a new framework of dealing with spatio-temporal relations. Now, of course, a little bit later, like Schrödinger comes up with wave mechanics, and his big discovery, compatible with Heisenberg, but it's very different. Like, namely, here the idea is that something wavy is underlying the behavior that we're seeing. And the analogy here is with wave optics in the 19th century. And so they famously didn't care for each other's views, like, you know, like Heisenberg calling wave mechanics disgusting, and Schrödinger calling matrix mechanics repulsive. But of course, like mathematical equivalence was rapidly proved, in part by Schrödinger himself, but then by Dirac, Jordan, von Neumann. And that kind of papers over like a very different way of thinking about the status of the state vector in the Hilbert space. Right? And I think roughly you can say that the descendants of wave mechanics are the ontic interpretations of quantum mechanics. Think Everett, the de Broglie-Bohm pilot wave theory, and the Girardi-Rimini-Weber spontaneous collapse theory. And the descendants of matrix mechanics are the epistemic interpretations, in where I would include Copenhagen, cubism, and now, like, you know, boobism. And so just a quick way of sort of showing, you know, what I'm after, like contrast Boop with Everett, right? So for Boop, like what the Hilbert space is doing for you, it's giving you the Born rule, but it doesn't represent stuff, right? In order to represent stuff, you need like some specific quantum applications running on this new quantum operating system, to use kind of the metaphor of Nielsen and Chang's book on quantum information. Now, for Everett, it's just the other way around. Hilbert space gives you stuff. You know, Sean Carroll like says, like, you know, the world is made out of wave functions, right? But it doesn't give you the Born rule now, right? I mean, so for that, they appeal to decision theory for agents in a multiverse. Okay. Now, so this is Oxford Everettians. There's also another class of Everettians, Berlin Everettians, like Christoph Lehner, who really have the courage of their convictions, who use like Hilbert space both to represent stuff and to get the Born rule. And of course, as a good Everettian, like, you take advantage of the fact that in a multiverse, you really can have your cake and eat it too. So now, for more careful exegesis of all of this, you know, I'm going to refer you to our book, where especially, like, you know, Mike Cufaro like lays this out like much more patiently than I just did. And I'm going to leave you like with one more version of this Dylan song. All right, I'm happy to take some questions if there's time.
Yes, we have some minutes for comments or questions. If you want to make a comment or question, please indicate it in the chat. I have a short question. Do you think that, or my real question is if you have some experience in the classroom with this type of topological approximation for quantum mechanics, Do you think that it can help in education?
I'm just making sure. Do you think the question is like, do you think that this way of thinking about quantum mechanics can help education?
No, that this form to present some results with the topological forms can help in education of quantum mechanics in the courses in the university.
Yeah, no, I mean, like I'm currently teaching a course on introducing like non-physics majors to quantum mechanics, where I very much use this approach that I showed you, right? And but I mean, it gives you like a particular way of thinking about quantum mechanics, right? It really pushes this idea that quantum mechanics is like the kinematics of quantum mechanics, right? The basic formalism is a new framework for handling probabilities, right? And that, in order to do anything else, right now you need to do dynamics, you need to like introduce like stuff, right? But what quantum mechanics is telling you that it has to behave according to the rules of quantum, right? So that's the view I'm pushing. Historically, what I find interesting is that if you now look at modern books on probability theory and statistics, is that Hilbert space methods are being used in these books. And somehow, like, so as a historian, I'm very interested, like how it came to be that there seems to be very little communication between people in physics using Hilbert space methods and people in general statistics using like Hilbert space methods.
Okay, thank you. And there is a question from Federico Holick.
Yes, thanks, Michelle, for this wonderful talk. It's always great to hear you. I always get really excited and I want to learn more about this approach. And my question is related to what is the stake or the take of your interpretation with regard to non-locality? Because if you interpret quantum mechanics as a new probability formalism, what can you say about the strong claims that the word is local versus the word is non-local? What will you say about that?
Yeah, so that's a difficult question. So what I would say is that in the spirit of what I showed you, is that like you would have thought that special relativity like requires you to like tell some story where you can like screen off like any correlation by something that by a common cause. And it turns out that the constraints are not that tight. You can have like a very a much more liberal constraint and still be non-signaling. In fact, you can go beyond quantum mechanics and you can have like PR boxes. And so I would say you just have to get used to the fact that you should resist the temptation that when you have these like correlations that cannot be dealt with sort of the standard way, screening them off by conditionalizing on common causes, that you think of these as just constraint produced by natures and not like, oh, Alice does one thing and then like it travels like instantaneously to Bob or vice versa. And if you go for this this epistemic route, that is easier, right? I mean, like I think a lot of students in quantum mechanics who like no matter how often you tell them that the Schrodinger wave function is not a field on ordinary space, still have this picture like, well, then you do a measurement and the whole thing goes poof instantaneously. And like now you're scratching your head, like, what is it that is traveling from like Alice to Bob that then like frustratingly you can never use to send a signal, right? And so I'm hoping that this approach will sort of prevent people like, from going down that particular rabbit hole in the first place.
Okay, thanks. It's clear. Yeah, I tend to agree. Yes.